In this example, we are required to calculate Gibbs energy at 40 degrees, and we have been given a delta H and a delta S, enthalpy and entropy. So we know that the equation for the Gibbs energy, delta G, equals delta H, the difference in enthalpy, minus T times the difference in entropy. And all we really need to do is we need to plug in our numbers, but we need to remember that the T that we have is always given in Kelvin, degree Kelvin, so we have to convert that. So our 40 degrees Celsius would be 273 Kelvin plus 40 Kelvin, and that gives us 313. So with these numbers we get delta G equals, we also need to remember that here we have kilojoule, whereas delta S is in joule, so we can write this as 3.94 times 10 to the power of 3 joule per mole. That's converted from kilojoule, minus our T, that is 313 Kelvin times 13.75 joule per mole and Kelvin. Now Kelvin cancels out, and we have both figures, both terms as joule per mole, which is a good sign because then we can subtract that. And if we put that into a calculator, we get delta G equals negative 0.36 kilojoule per mole. And since delta G has a negative sign here, this sign here is negative, it means that our energy of the system after the reaction has taken place is lower than it was before the reaction, and therefore, since delta G is smaller than 0, we can say the reaction is indeed feasible. Whether it happens or not in a reasonable time, that is a different story that we can explain with kinetics, but from a thermodynamic point of view, we know that in this case the reaction is delta G is negative, and therefore the reaction is theoretically possible. So thank you very much for watching, and I hope this makes sense.